Welcome to using the root test for convergence. So recall that the root test says for sequence a sub n greater than 0, we have that if the limit as n goes to infinity of a sub n raised to the 1 over n equals L less than 1, then the sum from n equals 1 to infinity of a sub n converges. We also have if the limit as n goes to infinity of a sub n raised to the 1 over n equals L greater than 1, then the series diverges. And finally, if the limit equals 1, then we can't tell, right? We need another test. So, for example, let's use the root test to determine the convergence of the sum from n equals 1 to infinity of 2n plus 1 over 5n plus 7, that whole thing raised to the nth. So here we have our a sub n would be 2n plus 1 over 5n plus 7, that entire rational expression raised to the nth. So if we look at the limit as n goes to infinity of a sub n raised to the 1 over nth, we are looking at the limit as n goes to infinity of 2n plus 1 over 5n plus 7 raised to the nth, and then that whole thing raised to the 1 over n. Here we can take advantage of our exponent rules. If we raise to an exponent and raise to another, we just multiply our exponents. This is actually simply the limit as n goes to infinity of 2n plus 1 over 5n plus 7. Another way of thinking of it is raising to the nth power and then taking the nth root. As long as we were looking at positive numbers originally, it'll just spit out the original number. This limit we do know, right? We have same degree polynomials, top and bottom. We just take their leading coefficients. We get 2/5. So since 2/5 is less than 1, we wind up getting that the sum from n equals 1 to infinity of 2n plus 1 over 5n plus 7, all raised to the nth, converges. Once again, let's go ahead and use the root test to determine the convergence of the sum from n equals 1 to infinity of 2 to the n over n. So in this case, our a sub n is 2 to the n over n. So we have that the limit as n goes to infinity of a sub n raised to the 1 over n is the limit as n goes to infinity of 2 to the n over n, all raised to the 1 over n. This is simply the limit as n goes to infinity of 2 over n to the 1 over n. This is one of those limits that is not so obvious, right? Let's just see what happens with that n to the 1 over n. So if we take the limit as n goes to infinity of n raised to the 1 over n, let's go ahead and call this capital L. Then we have that the limit as n goes to infinity of 1 over n times the natural log of n is equal to the natural log of L. This is the limit as n goes to infinity of the natural log of n over n should be equal to the natural log of L. Natural log of n over n is going to infinity over infinity. We can apply L'Hopital's rule. So we would have the limit as n goes to infinity of 1 over n over 1 is equal to our natural log of L. Limit as n goes to infinity of 1 over n is just 0. So we have 0 equals the natural log of L. And so that means that our L must be equal to 1. Natural log of 1 is 0. So we have, therefore, that limit as n goes to infinity of n to the 1 over n is just 1. So we can put that back in our original statement. That means that our original limit as n goes to infinity of 2 over n to the 1 over n, this should just be equal to 2 over 1, otherwise known as 2. So since this is greater than 1, we have that our sum from n equals 1 to infinity of 2 to the n over n must diverge. So here we have an example of a case where we could quickly prove divergence using the root test. And we had a case where we could quickly prove convergence using the root test. This first example with the 2n plus 1 over 5n plus 7 raised to the nth would not be particularly pleasant using the ratio test. So the root test comes in handy here. The second example, we could have easily done with the ratio test or the root test. So sometimes multiple tests are convenient. Sometimes you'll have to really be careful which one you're working with. All right, so that is some examples where the root test worked. In the next video, we will look at some examples where the root test fails.